Right then. So okay, right. Good evening, everyone. Is my voice clear?
Yes, sir. Good evening.
Okay, right. Yeah, good evening. Oh, thanks for joining the class today. We're supposed to have our class this coming Thursday, but somehow the test two is scheduled on the Thursday evening, so we have to, unfortunately, we have to do the class today to finish the syllabus that we need to cover. I do believe that somewhere we did miscalculate the number of weeks, or they bring the test to earlier. I'm not too sure. Has your solid lecturer already get in touch with you all when the class will be started for the second half of your subject here? No? Yeah. Okay. Yeah, I'm not too sure about that, but so anyhow, today we have to finish the syllabus. Then we'll do a revision as just like the test one earlier, and then at least your thermodynamics part will be completed. Okay. Right then. So I believe everyone is here. Okay. So then let's start our class. Okay. And you already seen the message in the group that, well, for the guy that shared the information, thanks for sharing that. So your test two will be on coming Thursday, 15th of May. The time would be 9 p.m. to 10:30 p.m. So it'll be 1.5 hour. The location will be P16 apparently. Okay. And since you are section 5, so you'll be going to the room demo 1 then. Okay. There'll be 2 questions for your test 2. Okay. The first question will be on, oh, it didn't say here. Okay, so the first question will be on the closed system. Okay, chapter 4 basically. But of course, to answer chapter 4, you need to understand chapter 3 because chapter 3 was the fundamental of energy. And the second question will be chapter 5, which is what we'll be covering today. It's an open system. Okay, so one question on one question on a closed system. One question will be on open system. Okay, and just to give you a heads up, one system will be in ideal gas, whereas the other one will be on non-ideal gas, which would be a pure substance. Okay. So 2 questions, 1.5 hours. Okay. So after we finish the chapter 5 today, as usual, today we'll break into 2 halves. The first half we'll finish the chapter 5, and then we'll look at the one past year question to perhaps helps you to understand how the test question might looks like, so you can prepare better. Okay. And before we begin, just also want to make an announcement. I received an instruction from the faculty that all the assignment has to be submitted through e-learning. Okay, so I see that a lot of you has already submitted your assignment 1 some times ago before your test 1. I do need you to resubmit that in the link in the e-learning. Okay, so everything in e-learning already being set up. So please resubmit your assignment 1 to the link on the e-learning. Okay, and for the second assignment, which will be the revision for your test 2, which is literally the past year question that we will be looking through today. So that has been uploaded to your e-learning as well. So please get it from there later on. And then after you do it, please submit that in the e-learning as well. Okay. So everything through e-learning. Don't submit through the share folder that I shared earlier anymore. Okay, because the faculty needs to to keep a record on all your summation. Okay, so please do that. And the due date for the summation for the assignment 1 and 2, I put it until next Monday. Well, anyhow, for your assignment 2 is for your test 2. So therefore, I think logically you should do it, get done before the Thursday anyway. Okay. Right then. So then we move into chapter 5. Okay, everyone can see the screen, right? Okay, right then. So chapter 3, we look at energy in general. What are energies? How do we define energy? What types of energy available? All the fundamentals about energy. Okay, and then chapter 4, we look at closed system basically. Okay, so for closed system, put it simple, there is no mass exchange. Okay, there can be work exchange, there can be heat exchange, but there is no mass exchange, which means the volume is constant. There's no mass go in, there's no mass go out. The volume is always constant. Okay, there can be work transfer to the system or out from a system. Heat can transfer in and can transfer out, but then there's no mass exchange. Okay? And in contrast to that, of course, for the closed system, we look at a pure substance. As a working fluid, we also look at ideal gas. So either closed system or open system, the working fluid can be any substance. If it's pure substance, if it's not ideal gas, then we have to refer to the thermodynamics table to find the property. Okay, but if it's a ideal gas, the gas which is light enough, then we can approximate it with an ideal gas equation. So it makes the calculation for the property slightly easier because there can be we can apply ideal gas equation to calculate the property. Okay. So today we'll be looking at open system. So it's a system that other than there's a energy, other than there's a heat exchange, today this system will have the mass exchange as well. Okay. So that's what the open system is. So when it comes to open system, the first thing that you should remember is the conservation of mass. Okay, we talk about this in the law of thermodynamics before this already. Mass is conserved, energy is also conserved. Okay, so when it comes, because there's mass exchange, so the number one rules that you must remember is mass is always conserved as well. Okay, we'll look at it in detail. What exactly does it mean by conservation of mass? Okay, and then also we have to be always mindful that our analysis, and as far as the syllabus concerned, we are looking at steady system. Okay, steady system means the change of parameter over time is 0, which means there's no parameter change over time. Everything becomes stable. It's steady, which means it doesn't change over time at all. Okay, and this is very important because if it's still changing over time, then we're talking about transient system. The analysis will be completely different. Okay? So we only look at steady system, which means time is not a function for us. We don't look at the system that change over time. Okay. And also, we will be applying the first law of thermodynamics, which is the conservation of energy. Okay, as the statement of the conservation of it's the conservation of energy. We'll apply that to the control volume. So we always have a control volume that we are analyzing. We're not analyzing everything. We always draw a boundary, system boundary. So within the control volume, we'll apply the first law of thermodynamics. The first law of thermodynamics, conservation of energy, and also conservation of mass, basically. Then we'll be able to solve the problem. The conservation of mass is not a concern in the closed system because there's no mass exchange. Everything is enclosed in the control volume. So there's basically no mass exchange. So we don't have to worry about conservation of mass. But now we're talking about open system. There's a mass in, there's a mass out. The conservation must be there. Otherwise, we are looking at a non-solvable problem. Okay. And then we'll be identify the energy, of course, because this chapter 3, 4, 5 is all about energy. Okay. So we're looking at the energy carried by the fluid stream across the control surface, the surface. So when the mass go in, how do we define the energy carries by the fluid? When the fluid go out, how do we define the energy brings out by the fluid itself? And if you still remember the full equation that we were using in chapter 4, we basically write it in a way that Q in minus Q out plus work in minus work out plus E mass in minus E mass out. So this whole thing equal to the change in the internal energy plus kinetic energy plus potential energy. Okay. If our system is not moving, right, the whole control volume is not like moving, there's no change in velocity, then kinetic energy is 0. If there's no change in elevation, the potential energy is also equal to 0. Okay. And in a closed system, mass, the energy due to the mass exchange is also 0 because in closed system, there's no mass exchange. Okay. But in today's open system, this will not be 0. So we need to know how to define the energy of mass. Sorry, the energy carried by the mass of the fluid itself. Okay, so that's what it means by the energy carried by the fluid. And that basically will be the sum of the internal energy of the fluid itself, the flow work, the kinetic energy of the flow, not the system. Okay, so these are for the system. The fluid itself, because it's moving, even though the whole system is stationary. Okay, let's say you imagine there's a box, there's a flow coming in, there's a flow going out. The box itself is not moving, so therefore it doesn't possess any kinetic energy. The box itself is not being elevated, so therefore there's no potential energy associated with the box. But then the flow is moving. Okay, so the E, the energy for the mass itself, because the flow is moving, so the flow itself has a kinetic energy. The flow itself might have potential energy. Okay, so the total energy carried by the fluid itself is a sum of all of them, basically. Okay, the same concept generally. Okay, but now we're talking about the fluid, the mass itself only. Okay. And then relate the combination of internal energy and the workflow. Sorry, the flow work, which is the work done by the flow. Okay, to the property of enthalpy. So we'll be looking at enthalpy today. Okay. And then we'll be solving the mass and energy balance problem for common steady flow device. So we'll be looking at a few steady flow devices. Okay. Specifically, we're looking at 4 only: nozzle, diffuser, compressor, and turbine. There are more, but then as I'm being told, that it's not in the syllabus of your subject here, because again, you are learning the very fundamental thermodynamics. So there's no point really to go into something too detailed. At least the steady flow devices has been covered. It gives you an idea how we analyze an open system. I think that will be sufficient. Okay, so that's what we'll be going through in the first half of today class here. Okay, so first of all, let's look at the conservation of mass. Okay, so conservation of mass is quite simple to understand. Let's look at this example here. So when you have 2 kg of hydrogen plus 16 kg of oxygen, okay, so in the end of the day, the combination of them, when they two mix together, I think everyone knows, you get to H2O. So eventually you get 18 kilograms. So the mass is always conserved. You can't destroy the mass as well. If it's in your control volume, it's there, it's there. You take it out, then it must become lesser. If you add more in, it becomes more. Okay, so the mass is always balanced. In a way, it's almost like the chemical equation, the equilibrium equation that you are writing for in your chemical class. So the mass is always conserved. Okay, and mass and energy, some of you probably know, is interchangeable according to this equation here. Okay, we wouldn't go into too detail like into it, but because they behave similarly, they can convert into one another. So therefore, when energy is conserved, mass must be conserved as well. It's as simple as that. Otherwise, where the mass would have gone, right? And in the closed system, as we say earlier, or we call it the control mass system, basically. Okay, so the mass in the system remain constant throughout the process. Okay, but for open system, because only the volume is controlled, only the volume is constant. Mass is not, because mass can come in and out. So we must always keep track the amount of mass enter and leaving the volume. Okay. And how do we define when it's moving, mass is moving? For sure, we're talking about rates, because then it's the mass flow rate. Mass is not stationary anymore. Okay, so the way we define the mass is basically, the mass flow rate is basically through this equation. Okay, it's the integration of the density and velocity over the area. Okay, because in the flow, especially let's say in a pipe, okay, I'll draw it as a pipe like this. Okay, so the velocity, if you look at different location in the pipe, okay, it will not be a constant velocity. Okay, there's always a velocity profile that looks like this. The velocity at the center of the cylinder of the pipe is always the highest, because at where it touched the wall, there is always a friction. So the velocity here is always 0. Okay, and then here is a V max. So this kind of profile is called the velocity profile. Okay, so which means the mass flow rate is also not constant. It should be the highest at the center, because that's where the velocity is highest. So the actual mass flow rate should be the integration. Integration means if you cut this area into a smaller section, each of it you can know the velocity at that point, and then you can sum them all together in a way. That's what integration means. Okay, but unless we analyze the whole system in 3 dimensions using finite element method, otherwise, most of the time, more conveniently, we're expressing the mass flow rate in this equation only. Okay, so we're taking a average velocity. So mass flow rate is as simple as density multiplied with the average velocity multiplied with the flow area. Okay, and A is a flow area. It's basically this area. Okay, the circular cross section of the pipe. that's where the flow is perpendicular to. Okay, and it's quite important to call this the flow area. It's labeled as AC here. Okay, it's sometimes they call it also the cross section area. Okay, so this is basically the flow area. Because there is another area that apply here, which is the area, the circumference. Okay, this flow area is basically pi d square over 4, okay, if this is diameter. Okay, there is another area, which is a surface, which is a pi d, the circumference, multiplied with the length. Okay, so this area, we call it the wetted area. It's an area wetted by the flow. Okay, not too much of your concern here, but this cross-section area is important when we analyze the heat transfer, because this is the area that come in contact with the surface, with the flow. Okay, so here we're only dealing with the flow area. Okay, but just to differentiate it, to let you know that there is actually another area called the wetted area. Okay, but for the flow rate, we'll be looking at the cross-section area that's perpendicular to the flow. Okay, and density is basically mass over volume. Okay, or in other words, it's also 1 over specific volume, because specific volume is basically the total volume over the mass. Okay, so this is another relationship that you probably will want to remember. Density is basically equal to 1 over specific volume. Okay, so this is volume flow rate. If we want to define the volume flow rate, then is really using this equation, because the definition of density can also be expressed in the rate. It's no problem. Okay, so then volume flow rate is basically m dot over the density. Okay, so then we'll get to velocity multiplied with flow area only. Okay, so volume flow rate is basically how fast this volume of air is moving inside the pipe. Okay, so it's either in meter cube per second or in kilogram per second only. Okay. So that's the how we calculate the mass flow rate and the volume flow rate. Okay, and when it comes to the conservation of mass, okay, you can imagine a bathtub like this. Okay, where one side you have the water flowing in, and then let's say you don't close the drain. Okay, of course, if you close the drain, you can notice the water sure will increase the water level. Okay, because the conservation of mass basically tell us that the mass in minus mass out equal to the change in the mass in the control volume. Okay, so in this case, the control volume is the bathtub itself. So that's our control volume. If you close the drain, which means there is no mass out and there is a mass in, so sure enough, this will increase, the water level will increase. But if you open the drain, which means this will not be 0, okay? If they are equal, which means you add the water as fast as the water flow out, then the water level will stay constant. Okay, but if you close the water now, you only open the drain, then this water level will sure decrease. Okay, so that's what conservation of mass basically means. Okay, so it's the change in the mass in the control volume is always the difference between the mass come in and the mass that goes out. Okay, and you can express it in the mass only, in kg only, or of course you can express it in the rate as well. The mass flow rate in minus mass flow rate out, it must equal to the rate of change of the mass in the control volume. Okay, so this equation is basically the conservation of mass equation, or the mass balance equation, sometimes we call it. Okay, it's a quite straightforward concept actually. It's not nothing too complicated. So it's just, in fact, thermodynamics are quite straightforward. It's just that you need to know which type of system, which principle apply. I think that is probably the more confusing part, which may need some times for you to get used to it. Okay. Then we talk about steady flow process or steady flow system. Okay. So steady flow basically means the parameter over dt equal to 0. Okay, and the parameter can be any parameter. In this case, it can be the mass. So which means for steady flow system, dm control volume over dt must be equal to 0. That's how we define steady flow system. dp over dt must be 0, no pressure change. dt over dt must be 0 as well. Okay, in fact, dE over dt must be 0 as well. Okay, so there's no change in the pressure, temperature, energy in the control volume, everything in the control volume. Okay, no change in the mass. Only then, over time, of course, then we can call it a steady flow system. The example just now, if you close the drain, you don't let the flow go out, there is the delta M in the control volume over time. So therefore, that is not a steady system. If you close the water tap, you open the drain, there is also a dm in the control volume over time. So therefore, it's not a steady system as well. Okay. If you have mass in equal to the mass out, they balance it out, then dm over dt equal to 0, then it is a steady system. Okay, so steady system basically means there's no change in the parameter. Sorry, no change of parameter over time. That's how we define steady system, steady flow system. Okay, so which means in steady flow system, for instance, like this, if here go in 2 kilogram per second, here 3 kilogram per second, then the one go out must be the sum of them, which is 5. Only then the dmcv over dt can be equal to 0. Okay, so in this kind of system, if it's a single stream, which means 1 in, 1 out, m1 equal to m2. Sorry, m dot 1, the mass flow rate coming into here, equal to here. Okay, if we write 1 for this, then m1 plus m2 equal to m3. Okay, this is a conservation of mass for this system. Okay, and individually, m dot 1 equal to rho VA at inlet number 1 here. Sorry, this system here, I have to draw it to be like this. Okay, so this is m dot 1, this is m dot 2. Okay, So the mass flow here is really the row 1, A1, B1. Here will be row 2, A2, B2. So if it's a steady flow system, then this must equal to this, because then the dm over dt in the control volume is 0. Okay. Multiple inlet exit, then it's a sum of all the inlet equal to the sum of all the outlet. Okay. If there's another fourth one here going out, then you must plus the M4. Okay. The only exception, in fact, not exception, just a special case, okay? This equation here basically means that density can change. When density can change, that basically means it's compressible or expandable, okay? The density basically means how much the mass in the same amount of volume. If you compress it, which means density will increase. If you expand it, which means density lower, okay? So when it comes to incompressible flow, which we know most of the liquid are incompressible, which means density doesn't change so much. So when density doesn't change so much, this equation got reduced to this. Okay, because now rho 1 equal to rho 2. Okay, so in the incompressible flow system, the volume flow rate is also equal to one another. Okay, but we don't call it the conservation of volume. This doesn't exist. Okay, it's just a conservation of mass under a incompressible flow condition, which makes the volume flow rate equal. Okay, between state 1 and state 2. Okay, but it will not be the case for compressible flow, because for compressible flow, density can change. Okay, so it's just a very special case only. So far, so good about the conservation of mass. Any question up until this point? Anything not clear? Okay. Right, nice. Right, I spent quite a bit of time to talk about the conservation of mass because that is the additional principle applied on top of what you learn in chapter 4 in order for us to look at the chapter 5 here, which is control open system. Okay, so let's look at one example here then. Okay, so here it says that a garden hose is attached to a nozzle. Okay, garden hose attached to a nozzle. Okay, I think everyone played this before. Okay, and we use that to fill a 10-gallon bucket. Okay, the inner diameter of the hose is 2 centimeter, and it reduced to 0.8 centimeter at the nozzle exit. Okay, if it takes 50 seconds to fill the bucket with water, determine two things. One is the volume and the mass flow rate of the water through the hoses, through the hose itself, not the nozzle. Okay, and second, the average velocity of water at the nozzle exit. Okay, so to put it simple, it is a, you can imagine like this. This is a nozzle. Okay, so this here diameter is 2 cm. Okay, and here the outlet D2 is 0.8 cm. Okay. And for us to find out the mass flow rate here, okay, so we don't know the mass flow rate, but then we know the volume flow rate of to fill up the water. So the volume flow rate, as you can see here, is basically the volume over the time. So 10 gallon of bucket, 10 gallon, if we convert that to liter, which is something that is more conventional for us to use, SI unit, okay? So 1 gallon is 3.78, okay? This, sometimes the conversion rate, just have to remember that, okay? If not, then the question should give you, or the question shouldn't be in gallon, in fact, at all. This textbook is from US because they are using gallon here, okay? But then from here, you know the volume that you're filling up in the time, which is 50 seconds. So from there, you can basically get the volume flow rate, which is 0.757 liter per second, okay? And mass flow rate is basically density multiplied with the volume flow rate. Okay, or the other way around, we write it usually is this. Okay, so we know this volume flow rate already. If we know the density, then we can know the mass flow rate. Okay, so density for water is quite standard. It's incompressible, almost incompressible, which is 1 kg per liter, or 1,000 kg per meter cube. Okay. 1 meter cube is 1,000 liter, basically. So therefore, you get 1 kilogram per liter. That's the density of liquid, of water, sorry. Okay, so then you multiply density with volume flow rate, you get to the mass flow rate, which is, this one is wrong, should be kg per second. So you get 0.757 kilogram per second. Okay, so that's the mass flow rate and the volume flow rate, which is what the question wants us to find out. Okay, through the hose. What about the velocity? If you want to find out the velocity inside the hose, okay, so that would be rho A V1. Okay, so density of water, which is 1,000 kg per meter cube. Area in the at the hose, diameter is 2 centimeter, so therefore pi 0.02 pi d square over 4. That will be the area of the hose, multiply with V1. M1 we already know. So then we'll be able to find out the velocity at the hose. Okay, but that's not what the question wants. The question wants us to find out is the velocity at the nozzle. And because this is a steady system across the nozzle, the bucket is not a steady system because the water level is changing, right? There's mass in. There is no mass out. So the bucket itself, if our control volume is a bucket, then it's not a constant. It's not a steady system. Okay, but for the hose, yes. Mass in equal to mass out. We look at across the nozzle, which is what I'm drawing here. Okay, so this is the dm control volume over dt is 0. The water from the hose come in, it goes out from the nozzle right away. Okay, so which means M1 equal to M2, M dot, same thing. Okay, now we're talking about the rate. So then M2 is equal to rho 2 A2 V2. Okay, density remain the same. Area, now pi, the diameter for the nozzle is 0.8 centimeter. So therefore 0.008 square over 4 V2. Okay, so then you'll be able to find out how much is V2, which should be this. Okay. So really when you analyze a system, it's quite important for you to look at where is your control volume, where is the boundary that you are analyzing. Okay, so here the focus is actually the nozzle. Okay, if we are looking at the bucket itself, okay, there is a M1 mass in. Okay, mass out equal to 0. Okay, so then mass in minus M mass out equal to dm cv over dt. Okay, so this is 0. So M1, which is this value, equal to the change of the mass in the tank. That's what we apply here, basically. Okay. So for the tank itself, it's not a steady system. There is a change in the mass. Okay, but across the nozzle, there's none. Okay, so that's what this example is trying to show you. Okay, so far, can you understand about this example? Okay, good. Right then, so let's look at the work from the flow then. Okay, so now we know how to find the flow rate, how to apply the conservation of mass. So next, let's look at how we evaluate the energy, the work done by the flow. Okay, so it's just flow moving. Okay, so how come there's any work? There's a question asking, is the 1 gallon equal to 3.78541 liter a fixed number? Yes. That is a imperial unit to SI unit, yes. The conversion is a fix. It's like 1 inch to centimeter. Okay. But don't worry, all your question in the test, in your assignment, everything will be in SI unit. You don't have to remember imperial unit conversion. And it shouldn't appear as well. Our syllabus is all SI unit. Okay, it just happened that this textbook use imperial unit. Okay, right then. So yeah, how just a flow moving. How is there any work involved? Okay, so you can imagine it like this. Okay, so you have a control volume already in your system. Okay, so when the flow goes in, it's almost like there is a imaginary piston pressing another volume of air into your existing control volume. And that's where the work actually happen, because it's actually literally like pushing new amount of air, new amount of fluid into your existing control volume. Okay, so then the work itself is basically equal to the F. Sorry, the force to force it, to push it in, is basically the pressure multiplied with area. Okay, and then the work itself is the force multiplied with the length, because F work is force multiplied with distance. Okay, so therefore it's P A pressure multiplied with the area, which is this area, the cylinder area. Okay, multiply with the length, how much the length is, it actually push it through. Okay, and this area multiplied with this length is basically the volume. So the work, the flow work, okay, this is called the flow work. Okay, we literally write as W flow is basically equal to the pressure multiplied with the volume. Okay, when you push the air in, which is equal to the mass in, okay, sorry, there's no rate here, so I should just write is in mass in. Okay, so mass in is pushing air in into the control volume. Okay, equally, if mass out, it's like the volume is pushing, the control volume is pushing the air out from it as well. So then we define the same way as well, pressure multiplied with the volume. Okay, just that now it's negative. When it goes out from the control volume, it's negative. Goes in is positive, basically. Okay, that's how we write the equation as well. It's always the, sorry, let me just go back to here. Okay, so you see it's always in minus out, in minus out. Same goes for here, in minus out as well. Okay. Okay, so that's basically what a flow work is, or flow energy, sometimes we call it. Okay, but this energy is really in terms of work, because it doesn't involve in the change in temperature. It's not heat for sure, so therefore it's a work. Okay, but that is not the total energy of a flowing fluid. Okay, the total energy in the flowing fluid is, we call it the E. Okay, total energy is equal to the internal energy of the fluid itself plus kinetic energy. U is internal energy plus kinetic energy of the fluid plus potential energy of the fluid. Okay, the fluid is moving. Okay, not the system kinetic energy. The system is stationary. The control volume is stationary. It's not moving. Okay, and it's not changing elevation as well. Okay, now we're talking about just the fluid itself. So the fluid is moving, for sure it possesses kinetic energy. Okay, depend on the situation, but most of the time there is no potential energy in the fluid. Okay, because it doesn't involve change in elevation unless there is. Okay, I think one of the example later on, you can see there's change in elevation in the fluid itself. So then there's a potential energy change. Okay, but the total energy in the fluid itself is the internal energy plus kinetic energy plus potential energy. Almost the same when we define the system as well. Okay, and if we write everything in specific form, which means over mass, okay, then it's U plus kinetic energy, specific kinetic energy, V squared over 2, and specific potential energy, gravity time altitude, Z, elevation, sorry. Okay. And then we can simplify it according to this here. Okay, because we want to make H, we want to introduce a new parameter, H equal to U plus PV. Okay. If we just leave it as it is, okay, the total energy of the flow itself, we write as theta, is basically equal to the flow work itself plus the E, okay, which then we can expand into like this. The PV from earlier, because it's moving, is pushing into the boundary, okay? So then we rearrange a bit. H is basically the enthalpy equal to U plus PV, which is this part here. So then the final equation for the total energy is basically enthalpy plus kinetic energy plus potential energy. Okay. Or we write it as this, H plus V squared over 2 plus GZ. GZ is a potential energy, basically. Okay. And we can also write it in the absolute terms, which mean M multiplied with usually M dot, yeah, equal to M dot multiplied with H plus M dot V squared over 2 plus M dot GZ. Okay, then everything we write in capital. So now this is H plus kinetic energy plus potential energy. Okay. Generally, we can write it without the mass, or we can write it with the mass. Okay, it's either the specific terms or the absolute terms of it. Okay, right. So this is the total energy associated with the flowing fluid itself, which is the E mass that you see earlier. Okay, which E? We just go back to here. This E and this E. Okay, of course, here is the absolute term. What we see just now is the E mass in. This is E mass out. Okay, over mass, it becomes the small capital. Okay. So then if we look at non-flowing system, which is closed system, and flowing system, okay. So for flowing system, of course, this theta equal to PV plus U plus KE plus potential energy. So then we make it into this. Okay. Whereas for non-flowing system, which is closed system, PV plus U plus KE plus PE. Okay, so PV is 0 because for non-moving flow, there is no workflow at all. Sorry, the flow work, not workflow. Okay, there's no flow work at all. So then it becomes U plus kinetic energy plus potential energy. Okay, so for non-flowing fluid, we definitely write as E, but then just to differentiate it, here we write as theta. Okay, but it's literally the E basically. Okay, so it's really the same E that we're talking about here. which is what you can see here. The E mass is really m multiplied with theta. Okay, if we multiply with m dot, which is flow rate, mass is just kg. If we're talking about kg per second, which means time come into picture, then we get the E dot mass. Okay, E is energy, so therefore you need kilojoule. E dot is the rate of energy change, so therefore kilojoule per second, hence kilowatt. Okay. When the kinetic energy and potential energy of the fluid stream are negligible, of course we cross it out, then we get to this only. Okay. So it's really just equation. If it comes 0, then of course we reduce to this. Okay. Sometimes we do calculate it this way because the magnitude of them one of them can be much more significant than the other, which means the kinetic energy, the velocity will be very small. So the kinetic energy is very, very small. Potential energy, maybe there's none at all. So therefore, reduce it to just the mass multiplied with the enthalpy. Okay. And this is applicable to both ideal and non-ideal gas, which means for all the pure substance that we're talking about. Okay. If it's because it's applied to pure substance, so therefore to get the H, we have to refer to the property table. Okay. For us to get the H. Unless if it's ideal gas, then we can. If ideal gas, then we can use ideal gas equation. Okay. Special case. Otherwise, all the time we have to refer to property table for us to get the property, the enthalpy, basically. Okay, so let's look at one example then. All right, another example that concerning this. Okay, so here it says that a flow steadily, the air flows steadily, okay, in the pipe at this pressure, this temperature, this velocity. Okay, so in the pipe like this, 300 kilopascal, 77 degrees Celsius, and 25 meter per second. Okay, maybe I should just write it properly. P1, 300 kilopascal, T1, 77 degrees Celsius, V1, 25 meter per second. Okay, and the flow rate M1 is 18 kilogram per minute. Okay, the question wants us to find out the diameter of the pipe. Okay, then the rate of flow energy, which means the flow work. Okay, this is the flow work. Okay, and then the rate of the energy transport by mass, which means the total E. Okay, transport by the mass. Sorry, rate of energy. So therefore E dot. Okay, the total energy in the flowing fluid. Okay, and then last, the error involved in part C, which is this one, if kinetic energy is being ignored. being neglected. Okay, because we know this should be E equal to this full equation. Sorry, this E dot. Okay, so it should be M dot H plus V squared over 2 plus GZ. Okay, but part B wants us to ignore this, then see what will happen. Okay, so one by one, let's start by finding the area. Okay. So the solution is here as well. Okay, but I myself probably will do it slightly different. Okay, so for me, M1 equal to 18 kilogram per minute over 60 kilogram per second. Okay, I always like to change to SI unit first, so I don't get confused. Okay, so this equal to rho 1 A1 V1. Okay, and this is A. Okay, so therefore A is, because A is ideal gas, so therefore the density I can calculate based on, sorry, I'll just write here because it's density for stage 1, P over RT. Okay, because for ideal gas, P1 V1 equal to M1 PV equal to MRT. Okay, so then mass over volume is P over RT, basically. It's ideal gas. It's A. Okay, that's very important. You have to know what is your working fluid, and then what kind of assumption you can apply to it. Okay. So then density I can find, no problem. Velocity, I have the number. So then I will be able to find out how much is my area. So that will be pi d squared over 4. So from there, I can find out my area, diameter. Okay, so then I can find out this, which if you try it, you should get this number. Okay, so later, the exact calculation, I'll leave you to try it later on. Okay, right then, so that's how we can find out the diameter of the fluid here. Okay. Second is the flow energy. Okay, so for flow, we know that is basically m dot multiply with PV. Okay, because is this equation. Okay, so then you can see here the solution, m multiply with p multiply with the specific volume. Okay, because we already multiply with the mass flow rate, so therefore this is the rate of the work. Okay, the rate of the flow energy. Yes, in fact, the question also asks the rate. Okay, so m dot p SI unit again. Okay, I myself, I would always write it in a SI unit. Okay, and then specific volume. Okay, and if you remember, specific volume is also equal to 1 over density. which density you already calculated just now. Okay. So from there, you'll be able to find out the rate of the flow energy. Okay, so that's how we find out the flow energy. And last is the total energy transport by the mass. So then we write the full equation here. Okay, of course, there's a plus PE as well, but then potential energy, since there's no change in the elevation in the flow, so therefore it's basically zero. Okay, and then here, the enthalpy, instead of looking from thermodynamic table, because it's ideal gas, so then H equal to Cp multiplied with T. It can be approximate to Cp multiplied with T. Cp is the constant specific heat, constant pressure specific heat. T is the temperature. So then if you calculate everything, you should get this number. So that is the total energy transport by the mass. Okay. Flow energy plus internal energy plus potential energy plus kinetic energy. Okay. Internal energy plus the flow energy, of course, equal to the enthalpy. So that's how we evaluate it. Okay. And D, the question wants us to ignore the kinetic energy. If we recalculate again without the kinetic energy, you find out this number, which is not very far off from this. Okay, the error is only 0.09%. Okay, because the magnitude of the enthalpy is much larger than the kinetic energy. So depend on the situation. Sometimes the enthalpy is much larger, so then makes the kinetic energy insignificant. Okay, but the best is to calculate them, even though the magnitude is small. If it's there, usually we just calculate it. Okay, in this case, like it's very clear, there is no elevation change. So therefore, PE is zero. Okay, but kinetic energy definitely is there is a kinetic energy here. Okay, so even though it's small, sometimes most of the time we'll just calculate it. Okay. Right then let's look at another example. Yes, one more example before we move into the energy analysis for steady flow system. Okay, so quickly here. Now this is a steam. So a steam is a pure substance. It's not ideal gas. So therefore, any property we have to look from the steam table, the thermodynamic table. Okay. So here it says that steam is living at a 4-liter pressure cooker. Okay. Operating pressure 150 kilopascal. Which means inside here is 150 kilopascal. Okay. It is observed that the amount of liquid in the cooker has decreased by 0.6 liter in 40 minutes. So then that gives us the volume flow rate basically. Okay. After the steady operating conditions are established. So this is under steady state condition. Okay. So then the volume flow rate is 0.6 liter over 40 minutes. That's the volume flow rate. Okay. And the cross-section area of the opening is 8 millimeters square. Okay, so cross-section area is available. So what is the mass flow rate of the steam and the exit velocity? That's what the question wants us to find out first. Okay. Second, the total and the flow energy of the steam per unit mass. Which means the question wants us to find out the E and the flow energy, which is the W flow. Okay, total energy I'll just write as E. Or earlier they write as theta. Okay. And then number third, the rate of which energy leave the steam cooker. So which means this will be the total E dot temp. So three things we have to look for it. And because this is steam, so therefore we have to look at the property table. Okay. So if we look at the property table, okay, you can see here the property. Okay. So at 150 kilopascal, okay, Vf this value, Vg this value, Ug this value, Hg this value. G is the gas, F is the fluid, saturated liquid, saturated vapor, saturated vapor, saturated vapor. Okay. So we know the volume flow rate, but then we have to change it to mass, basically. Okay. So then, which means we have to multiply with density, or 1 over V. Okay. And because this is steam that exits the cooker here, so therefore this is for the fluid itself. Okay. So then from there we get this number 0.5, and over 40 minutes, then therefore we'll get this. Okay. So that's how we get the mass flow rate, basically. So it's really just changing the unit only. Okay. And then how about the velocity? So the velocity is basically rho a v. Okay. And rho excuse me. Okay. Okay. Sorry, here we are using the density for the fluid because the question say that the amount of liquid in the cooker is decreasing by this much. So this volume represents the volume of the fluid itself, the liquid itself. Okay. So the mass go out equal to the mass here. Okay. So this is equal to M1, also equal to M2, or more specifically, equal to Mg, equal to Mf. Here is the gas, here is the fluid. Okay, so same number here, we can apply for the gas. Okay, because the opening is 8 millimeter. So this area here, we have 8 millimeter square, which what goes through it is actually the steam. So it's the gas. Okay, so from there, we'll be able to find out what is the velocity. Because the rho for G, this can take it as 1 over V G as well. Okay. So then we'll be able to find out how much is the velocity of the flow, of the steam that run through the opening. That's 0.0, the 8 millimeter square of area. Right, so that's how we find out the flow rate and the exit velocity. So then is the total and the flow energy. Okay, so maybe let's find the flow energy first. Okay, so the flow energy, oops, it's not written here. Okay, so the flow energy, okay, is actually equal to PV. Okay, and we also know that H equal to work, the flow energy plus internal energy U. Okay, so therefore, for us to get this, is basically H minus U. Okay, and we're talking about the one that goes out is the gas, so therefore we are using the property of the gas to calculate this. Okay, which if we look out from the thermodynamic table, we have the Hg and Ug, the saturated vapor, basically. That will give us this. Okay, and then the total energy, theta, is defined by this, H plus kinetic energy plus potential energy. Kinetic energy is close to 0, as we know. Okay, so we can approximate it equal to H. This is definitely 0, or we can include that as well. It's not a problem. We already have this. So this can be the V G over 2. Okay, so then you get a additional 0.588 to this. Okay, so again, for me, I will just include that in, since we know that it's always enthalpy plus kinetic energy plus potential energy. And then the rate of which the energy leaving the steam cooker, the cooker by steam, okay, is basically this theta multiplied with the flow rate, then the flow rate that we calculated earlier. Okay, then we get the actual kilowatt of energy, the rate of change of energy leaving this pressure cooker through the steam, basically. Okay, right? So that's how we can solve the question, really. So time is about finding the state, basically. How do we find the state? Then we'll be able to calculate the parameter. Okay. Right then. Any question up until this point? Is everyone still following me? understandable, right? I do realize it's a bit boring. It's a thermodynamics after all. Okay. Well, I hope you can understand well. I think that's the most important. Okay. And then going back later on, you can give it a try again on this example by yourself. Okay. Okay. Right then. How to know V represent velocity and volume? That's a very good question. Um, mm, mm. I would say, yep, I think throughout the note here, if its velocity is this writing of V. Okay. Whereas for volume is this yes, is this a curvy volume V. So this is volume, this is velocity. Yes, it's a bit difficult to differentiate. Yes, I agree. And there is no specific velocity. There's nothing so-called specific velocity. So therefore, yes, you don't have a small cap velocity. So all these curvy V are standing for volume, specific volume. The small cap curvy V, specific volume. The large curvy V is the total volume without the serif. It's the sans serif font. Is that okay? Okay. Well, a lot of time in thermodynamics especially, we're running out of a symbol to represent. Okay. In this, sometimes we do use U to represent velocity as well, but in this case, we can't because there's internal energy using U already. Okay. So yeah, the volume is the curvy sans serif V, whereas the velocity is a serif V, the straight V. Okay. Right then. So I think let's look at how we analyze steady flow system then. Steady flow open system. Okay. So we look at how we define energy already. The work, the flow energy. Okay, the flow work basically, and then the total energy in the flowing fluid. So we look at conservation of mass, we look at how we define the energy of it. So then let's apply that to a steady flow system then. Okay, so steady flow system, basically volume is constant, mass is constant, energy is also constant. Okay? So the conservation of energy, conservation of mass has to be applied. Okay? And the fact that volume is constant means that boundary work is also zero. Okay, boundary work is the expansion of boundary. That the work done by the boundary itself. Since now the boundary doesn't expand, volume is constant, so therefore boundary work will be zero, unlike the closed system that we learned before. Okay, so here there's no boundary work, but then we have a flow work. Okay, so steady again is no change in time basically. Okay, so then the equation that we are applying here, okay, pretty simple. It is still okay. I'll just write the E mass as E, so is shorter a bit. Okay. Okay. Right, and then because this is the system, potential energy, system kinetic energy, as long as this system is not moving or there's no elevation change, velocity zero, elevation change zero, so then we have this to be zero. Okay, and because it's a steady flow system, so the change in the energy is also constant, so therefore this is constant as well. Okay, which is why here we also write as zero. Okay, so really what we end up with is everything here equal to zero. So this has to be balanced across, as simple as that. Okay, which is why if we rearrange it, what we'll get is Q in plus work in plus energy due to the flow carried by the flow in has to be equal to the energy out, work out, plus the flow energy carried by the flow going out from the system. Okay, so it's really in equal to out. Conservation of mass, conservation of energy combined together. Okay, so that's the equation that we'll be using to analyze a steady flow process or steady flow system. Steady flow open system. This is the equation that we'll be using. Okay, and m dot theta. Okay, so m dot multiply with enthalpy plus kinetic energy of the fluid, not the system, the fluid itself. Okay, plus the potential energy of the fluid. Okay, same goes for this side. So this is the one that we were looking at just now, how to define the energy in the flow. So now we apply it here. Okay, so the whole system basically is still based on the equation that you seen in chapter 4, basically. Okay. And sign convention, well, I think the easiest is If the work go in, energy go in, then it's positive. If they go out, it's negative. I think that's much easier to remember. Okay. And of course, everything can be expressed in specific term as well. It's not a problem. Okay. If we divide over mass flow, depending if we are talking about the rate of energy transfer, we divide it by mass flow rate, then we get the specific heat. If you're talking about the power, rate of energy transfer, rate of work transfer, divide by the mass flow rate, then we'll get the specific work, basically. Okay. So this equation really can be in the absolute terms or in the specific term. Okay. So let's look at a few steady flow devices then. Okay. In fact, there's actually quite a few example, so it's quite long. And I notice it's already 9:30, so I trust that it's also quite tiring by now. So why don't we take like a 10 minutes break? So now it's 9:37, let's say 9:40. Okay, so let's come back by 9:50, go refresh yourself, then we'll go into the steady flow devices. Is that okay?
Yes, okay.
Okay, right. So I'll see you in 10 minutes time.